Hey guys, want to do some problems here, and this is for test 4, just a heads up, some different stuff. Let's see what we got in here, and we'll run through these like usual. Here we have a car that's moving 30 meters per second, and it says that the wheels have a radius of 0.3 meters. So don't forget that you've got those three little expressions that get you back and forth. The first one is S equals R theta. Second one, V equals R omega. Third one, A equals R alpha. These are our old friends, displacement, velocity, acceleration. You could also write this X instead of S if you need to. S is a little more generic, so when we're moving in a circle, you know, X kind of sounds like a straight line, but either one's fine. These are the new variables: theta, the angle of rotation; omega, the angular velocity; alpha, the angular acceleration. But I can always get back and forth between those if I need to. So right here, when they say that the velocity is 30 meters per second and the radius is 0.3 meters, and they want the angular velocity, not too hard to come in here with this guy. And V equals R omega. Omega would be equal to V over R. Just do the little division there. Number 2 here, a drill turns at 100 radians per second. Looking at the unit, if it said meters per second, that would be a regular velocity. This is radians per second, so that's an angular velocity. And furthermore, it's the angular velocity at the beginning of the problem. So here's 100 radians per second as omega naught. It spins up to 1250 radians per second, another angular velocity, the final one there. And the time is 6 seconds. They want us to find the angle theta right there. Now, I don't have an expression that links these together. If you think about the kinematics, the rotational kinematics formulas, we've got omega equals omega naught plus alpha t, and theta equals omega naught t plus 1/2 alpha t squared, and omega squared equals omega naught squared. And it doesn't, plus 2 alpha theta, it doesn't take a whole lot of searching to see that none of those have these 4 in them. So that's not going to work. What I could do, though, is realize that I have this one, and this one, and I could get alpha, and then I could take it down here, plug that in, and I would have this and this and this, and I could get that theta that I want right there. So that's the game plan with this one. First half of this, you'd have to go get alpha, like that, and then you could put it into theta. Okay, kind of 2 steps going on there, and but that should be fine. All right, the numbers are there. You can do that. Here's number 3. I got a 170 kilogram merry-go-round, and that would be the mass. I'll go ahead and start a little list here. 170 kilograms. The radius of the thing is 2.2 meters. So I'm kind of picturing this in my mind. You go out to the playground, there's one of these discs. Usually there's some handrails or something, but we'll forget about that. This thing is spinning right there. In this case, we're going to put a force of 200 newtons on it. So oh yeah, I'm over here now. Forgot about that. Hang on just a second. Let me move this where I can get to it. Kind of outsmarted myself there. So I'm picturing this force at the edge. You know, I'm pushing this thing sideways. Force, please. Man. So here, somebody pushing on the edge, 200 newtons. And since we already know the radius is 2.2 meters, see how that turns into a torque, a force at a distance that causes rotation? That's torque. So torque causes rotation. We want to rotate this thing. That makes us think about torque. Torque is R times F. I've got R, I've got F, so I should be able to get the torque here. The other thing that I know about torque, the other expression, is that torque equals I alpha. Okay? This is kind of like Newton's second law, F equals ma. Instead of force, I'm thinking about torque. Instead of acceleration, I'm thinking about angular acceleration. And it's not the mass of the thing, it's the moment of inertia, that number that tells me how easy, how hard it is to spin this thing. Well, this is a flat cylinder, a flat disc, so I could go to the table and look up the moment of inertia of that, or on a test, you know, that expression would be given. There should be a little table with all those in it somewhere. So I've got that. Anyway, if I take this part right here and substitute it in for torque, then I would have RF equals I alpha. We're looking for alpha over here, so I need to divide by I, like that. And this would be 2.2 meters times 200 newtons. I'm dividing that by I. Whoops, haven't calculated I yet. 1/2 times 170. You could do this over here on the side, or you could just plug it in down here. Actually, that's kind of nice, because see, then I'd have an R on top and an R squared on bottom, and some of that stuff would cancel out. It's better to kind of put it all in one place, but I'm doing it over here today. Go ahead and get that number and put it down there on the bottom and see what you get. 0.5 times 170 times 2.2 squared, don't forget to square it, would be 411.4. That is a number that tells me how hard it is to spin this thing. And the units there, of course, would be kilogram meter squared. And then you could finally do that thing. Remember, we were just getting this I and putting it in down here. But there's the whole deal. And I'll just come in and get you a number real quick. 2.2 times 200 divided by that last number. Second answer, we'll pull that back up, would be 1.07, 1.1. And that's going to be radians per second squared right there. If you want to see the gory details of that, I've got meters and newtons on top. I got kilogram meter squared on the bottom. So this is what happens with that. The meters, the newton is actually a kilogram meter per second squared. And then on the bottom, I've got a kilogram meter squared. So this kilogram cancels that kilogram. This meter times this meter is a meter squared, and that's going to cancel this meter squared. So the only thing I'm left with is nothing over second squared, except it's not really nothing. That's where that radian jumps back in right there. So 1.1 radian per second squared would be my units on that. Number 4 here. We want to go to the next one, please. What's happening? Oh, well. A round length of metal rolls on level ground at 3 meters per second. Then it's going to roll up a ramp and stop at a height of 0.92 meters. Oh boy, is the metal solid or hollow? Well, let's find out. Here goes the level ground. Here's the ramp, and the object is here. And then it's up here. You see how that's one object at 2 points? And immediately we remember what we did on the last test with conservation of energy. Because anytime I've got one object at 2 points, it's probably a conservation of energy problem. And indeed, this one is one of those. Okay, so I need to think about all the forms of energy here and all the forms of energy here and make sure that those are the same number. Well, down here, the height at point 1 is 0. And they tell me up there that it's rolling at 3 meters per second. So those would be the numbers that I have. Up here at 0.2, it stops at a height of 0.92 meters. And since it stopped, the velocity would be 0. Okay, so that's the information that I have here. And all I got to do is come up with all the forms of energy at this point and that point. Now, typically, that's just potential energy plus kinetic energy. So usually we would write mgh1 plus 1/2 mv1 squared equals mgh. You know what? I'm not going to have enough room here, so let me bring that down here. mgh2 plus 1/2 mv2 squared. But this one's got one extra little trick to it. That pipe is doing two things at the same time. It is simultaneously moving forward in a linear, the center of mass of the pipe is moving to the right, and at the same time the pipe is rotating. I've got two kinds of motion there. The pipe could be sliding, and I'd have this kind of kinetic energy, or it could just be rotating and I'd have the other kind. As it is, it's rolling, so I actually have both. And I need to put in something here that we don't usually put in. I need to put in a plus 1/2 I omega squared. This is the potential energy. And since H1 equals 0, that's actually going to go away. Here is the old kind of kinetic energy, where the forward motion of the object, but now I've also got this rotational kinetic energy. So I got to put that in too. It's down here. It's not up here because the velocity is 0. V2 equals 0. This one goes away. Even if I did put it in, since it's no longer moving, then it's no longer rolling. So the angular velocity at 0.2 is also 0, and that one would go away. All right. So it's going to look something like that. All right. And just trying to clean that up. We've got a couple extra steps we got to do here, a couple little substitutions and stuff, because we're not to the point where we can do this yet. But I'm going to put it all here. And then this I need to fill in for that. Well, this is a round object, and there's kind of two choices. If the thing were solid, then I would be equal to 1/2 mr squared. And if it's hollow, then I equals mr squared. What that means is that a solid piece of pipe, or a solid cylinder, and a hollow cylinder do not roll the same. This guy is easier to roll. The solid pipe has half of the moment of inertia. If you put the two side by side and rolled them down a ramp, then the solid one would win. It would come out ahead because it's going to spin easier. On average, the mass is closer to the center of that thing, which makes it easier to turn. The farther away the mass gets, the harder it is to spin. So on the hollow pipe, it's all out at the edge, and here it's all the way to the center. So on average, it's closer to the center there. All right, so I don't know which one it is. That's essentially what they want me to do. There are two ways you could approach this problem. One would be to say, well, I'm going to guess it's solid, or I'm going to guess it's hollow, and put in that moment of inertia for I right here, and then see if it's right, see if it comes up. Okay? Plan B would be to come in here and say I equals some number. Let's just call it C, mr squared. And then we could solve it for C, and the C is either going to be 1/2 or it's going to be 1. And if I get a 1/2, I know that the pipe is solid, and if I get a 1, I know it's hollow. So that might be the easiest way to do it. Let's try that way. If you don't like it, you can do it the other way. Just pick one and put it in. But this is kind of a slick trick, so let's see what happens. There's my I right there. So I'll put some little parentheses just to say that's what used to be I. The omega here, they did not give me the omega. So I need to make a little substitution right here. And what I know about since I've got the velocity, I know that v equals r omega, so omega would be v over r, only I really want omega squared, so that would be v squared over r squared. And if I take that and put that in for omega squared right there, then this would give me a v1 squared over r squared, like that. Let's go ahead and finish this up. Here's equals mgh, so that'll go in right here, like that. All right. Now, a whole bunch of stuff cancels out, which is good. I don't know the radius of this thing. Turns out it doesn't matter because I've got an R2 on the bottom, which cancels the R2 on the top. I don't know the mass of the pipe, but now, since we made all those substitutions, m, that's everywhere, so that'll cancel out. And I think we're getting somewhere here. I've got this 1/2 v1 squared. I've got 1/2 c v1 squared, and that's equal to gh2. And I know the v1, and I know g, and I know h. The only thing I don't know is that c. So if we could solve for that, then we could get that number and see what we're going to be. I'm going to subtract this from both sides, and that'll leave me 1/2 cv1 squared equals gh minus 1/2 v1 squared. I need to multiply through by 2. So cv1 squared equals 2 gh minus 1/2 v1 squared. That'd be a great place to distribute that and get rid of that fraction there. But let's also divide by v1 squared. So that'll take this off of this side. I wouldn't normally do this, but I try to give you some more steps here, but I'm out of room in the worst way. So let's strike, and now you're going to let me get in there and do it. Alright, we're going to have to, never mind. C is, let's distribute this as we go. 2gh1, I'm sorry, 2. I'm distributing the 2 here, so 2 times that, 2 times this, I'd cancel the 1/2. Minus v1 squared over the v1 squared, like that. And hopefully that'll come up either 1/2 or 1. And we can see what we got. I'm going to put some parentheses around the top. 2 times 9.8 times the height here was 0.92. And then I'm subtracting the 3 meters per second. That's got to be squared. I close up the numerator and divide by 3 squared. And it's a 1. Okay? So we just found C. C should be a 1 right there. And remember, if I get a 1, it's a hollow pipe. So that's what we've got here. Again, not the only way to do that problem, but works pretty good. Here's number 5. Excuse me. Helicopter blade, length of 11 meters from end to end, spins in the middle. So I'm thinking about a helicopter blade like this. Here's the rest of the helicopter, not that it really matters. And then the length of this thing is what they just gave me. L equals 11 meters. Okay? And the mass of that helicopter blade is 110 kilograms. What torque do I need? How big of a motor do I need to put in this helicopter to get this thing to go here? I need an acceleration of 3 radians per second squared. So that would be alpha, my angular acceleration. Looking at the units there, it's not meter per second squared. If it was, it'd be regular acceleration. But radians per second squared would be angular acceleration right there. They're looking for the torque. So the thing that I know about torque is that it's equal to I alpha. This is what I'm looking for. I've got alpha. If I could find some way to calculate I, then I would be in good standing here. And we do have that. The moment of inertia of a long skinny object is what, 1/12 ml squared? And so using that, we can make this work just fine. Here's 1/12 ml squared times alpha, 1/12 of the mass, 110 kilograms. The length is 11 meters. That has to be squared. Need to multiply by alpha, which was 3 radians per second squared. And that's the torque of that engine. They didn't used to really rate engines in torque. I guess somewhere they might have, but like lawnmowers and that kind of stuff. You used to go to the hardware store, to Sears, whatever, and buy a lawnmower, and it was all rated in horsepower. And they got away from that. Now it's in torque. It's actually foot-pounds instead of Newton meters. But it's a good way to measure how much torque, how much ability to spin an object a motor has. Horsepower, you can kind of cheat on it, and the companies were kind of cheating, and it depends on the temperature of the motor and air consumption and a whole bunch of other factors that you don't really want to think about. Okay, number 6, I got an ice skater. She's got a moment of inertia 1.2. I don't have to look it up on a table. It's already there. But she's going to stick her arms out. So she starts out spinning like this, and her moment of inertia I is 1.2 kilogram meters squared, and there she spins away like that. 2 radians per second would be the angular velocity. And then she's going to put her arms out. Ooh boy. I don't know why that was hard to draw, but whatever. And that is going to raise her moment of inertia. The farther the mass gets away from the center, the more moment of inertia there is, and it makes it harder to turn. So she's going to slow down here. She has to. If she pulls her arms back in, she'll speed back up again. She has to conserve angular momentum, and that's where this problem goes. Conservation of angular momentum. It's very much like conservation of regular momentum. It's just a spinning kind instead of a straightforward motion kind. So I need to write L equals L prime. That's the symbol for angular momentum before and after she puts her arms out. L is I omega. Remember that regular momentum was mass times velocity. So the angular momentum, instead of mass, I write I. Instead of velocity, I write angular velocity. So all I have to do here is I omega equals I prime omega prime, like that. I've got 3 of those numbers, and I should have put I prime and omega prime there. But omega prime is going to be equal to I omega over I prime, like that. And you put the numbers in, and you got it. And yep, she slows down. Number 7, find the gravitational attraction between a red rubber ball and a yellow lemon. All right. So these 2 things, remember that any 2 things with mass are going to pull on each other. So we'll put in the red rubber ball right there. And I've got a nice yellow lemon over here. Kind of hard to see because it's yellow, and yellow, as bright as it is, just doesn't stand out well on the white. All right, but they give me some numbers here, some masses. The mass of the first object, the red rubber ball, is 7.2 grams. And of course, we don't like grams. 0.0072 kilograms is what we want to do. Mass 2, the lemon, would be 237 grams. And again, that would be better expressed as 0.237 kilograms. They are a distance r of 1.1 meter apart. All right. And I don't want to take half of that. We want the whole distance. But gravitational attraction, Newton found out for us, is equal to gm1m2 over r squared, like that. So here's the value of the universal gravitational constant, like that. That should be measured in Newton meters squared per kilogram squared. first mass is 0.0072 kilograms. The second mass is 0.237 kilograms. And I'm dividing down here by that distance of 1.1 meter squared. All right. Just checking the units. There's a meter squared on top, meter squared on the bottom. Those go away. Here's a kilogram, kilogram, make a kilogram squared, cancel that kilogram squared. The only thing left is going to be newtons, and you can go get the number for that. All objects that have mass exert a gravitational pull on each other. With a red rubber ball and a lemon, it's going to be an exceptionally small number. You see this 10 to the negative 11 right there? And these are fractional numbers, so this is going to come out a little bitty. But that's okay. We don't see red rubber balls attracting lemons into their orbit or anything. If it's a star and a planet, then it makes a big deal here. The ISS station something. I meant to cross all this out. I was cutting the problem down. I got left in there. The ISS, the International Space Station, moves in circular motion due to gravity around the Earth. So here's the Earth. Here's the International Space Station. And it's in gravitational orbit around the Earth. Anything moving in a circle has got to have what we call a centripetal force. So I am fully expecting this thing moving in a circle to have a pull on it toward the center of the Earth. I got to have that. That is F sub c, and it's my duty to go say, where are we going to get that from? Is there a little string and there's somebody on Earth that's pulling it? No. There's no string, no person pulling. What's pulling is gravitation. Earth's gravity is the string, if you will, the force that pulls toward the center. So I need to take the expression for centripetal force, which would be mv squared over r, and I need to take the expression for gravitational force, which would be gm1 m2 over r squared, and set those equal to each other because the centripetal force is the gravitational force. Those are the same thing, and if they're the same thing, then they are equal, and set them equal to each other. Now, one of these objects, let's say the Earth is m1, and the other one, International Space Station, is m2. This m is the rotating object, the object that's moving in a circle, in orbit, whatever. Okay? So this one would have to be m2, and it's never going to let me put 2 right there. But you can see that this m2, I got it, is going to cancel this m2 right there. And this r will cancel one, but not both of these r's. So I'm already down to this right here, like that. So let's look and see what we know. G, that's a constant. 6.67 times 10 to the negative 11. I got that. Mass 1. What's left? Oh, the Earth. And they gave me that mass right there. So I got that. 6 times 10 to the 24 kilograms. R, this is not the radius we want. This is the radius of the Earth. That would be the distance from the center of the Earth. I'll pull that out. From the center of the Earth to the edge of the Earth, like that. The number they want, what they're asking for, would be the distance from the surface of the Earth out to the International Space Station. There it goes. They want this distance right here, not this distance. And what the formula actually gives us is from the center out to the edge. So I'm going to call that R, and just leave that R right now, like that. I've got, the formula is going to give me that. So that's what I'm looking for, like that. I don't have V, though. So we're going to have to use a little bit of geometry here and think about what we know. A little bit of physics, a little bit of geometry. V is distance divided by time. And this is the International Space Station is making a circle here. The distance of a circle is 2 pi r. and I've still got that time on the bottom. So that's the expression I want to work into that. And you notice that this is actually v squared. So v squared would be equal to 2 pi r over t squared. That would be 4 pi squared r squared over t squared. Just square each one of those things. Let's put that in for v up here. 4 pi squared r squared over t squared equals g m1. Oops, not you. Up here, m1 over r, like that. Okay? So that takes a little bit of doing here, but the basic idea is that I got to have a centripetal force. I'm getting that from gravitation. Set up the expressions for that. And then since I don't know v, go get v and put it in. And you want to do all that before you do anything else. Because see, now I've got some r's here and some r's there. So what I'd like to do now is to come in here and multiply both sides by r. That's going to cancel here. And when I multiply by r, then r squared times r is going to be an r cubed. Put those together. Simultaneously, let's multiply both sides by t squared. Cancel the t squared here. And it'll come up over here on this side like that. So when the dust clears from all of that, what I'm going to have is 4 pi squared r cubed equals g. I have a hard time making my g's and 6's look different. m1 t squared r cubed is going to be g m1 mass of the earth t squared divided by 4 pi squared, like that. And I don't want r cubed, I want r. So if I take the cube root of both sides, then I can get that. So that's where we want to go with this thing, and I think I've got enough room here, yikes, to finish this up. R equals the cube root of g m1 t squared over 4 pi squared, like that. All right. Now there's actually one more step of this, so let me press on just a little bit here. I need to do a cube root. I don't have a cube right here, but I do have that math menu. And if you hit the math menu under number, go one step to the right, and then you can come down here. Whoops, I'm sorry. Right there. It's on the math menu. Number 4 there. That's the cube root. Okay, hit the math button. It's the 4th one down. And I want to do the cube root of g, which was 6.67, e negative 11, times the mass, 6 times 10 to the 24, times the time, which is 93 minutes. We don't like minutes, do we? We want seconds. So we need to do one more little thing right here. 93 minutes. 1 minute is 60 seconds. So we actually need to put that together and square that. I can do that right on the calculator right here. I'm going to put in some parentheses and go 93 times 60. And then I'll square that, and it'll square the whole thing for me right there. So that's good. I need to divide by 4, divide by pi squared. And there's a pretty big number. Okay, that is the radius. Well, how many decimal places I got there? 6,808,000. 6,808,000 and some change. 664 meters. Okay, that is r. That's the distance from the center of the Earth to the center of the International Space Station. That's not quite what we wanted, is it? They told us that the Earth's radius is this number, so we still need to come back and take this away. If I take that number and subtract 6,371,000 meters, then I'll get the number that we're looking for. There's from the center of the Earth to the center of the International Space Station. I want to start at the surface of the Earth and go up, so let's subtract the radius of the Earth. and I'm going to get about 438,000 meters. I could also write that 438 kilometers. And just for kicks here, if I multiply that by 0.6, I'll get the number of miles. So about 263 miles above the surface of the Earth is where that is. This would probably be the best answer for a physics class because we like meters, but just kind of for reference there, you know, it is 93 minutes that the thing goes around. That's pretty crazy. Every hour and a half they make another orbit, and that means that they have to be at that height. Okay, here is come on, number 9. I got a car on a curve. It's going through a curve. There's a bank angle. Now there's a formula for bank angle. The bank angle formula looks like this. Here's the car on the bank going around the curve, and that angle right there is all important. The more I tilt that up, the more it helps me get through the curve. So I write tan theta equals v squared over gr. I don't know if I did that on the video for you or not, but let's think real quick about this. Gravity is going to pull straight down. Like that. And the normal force pushes up perpendicular to the surface of the ramp. That's got two components, a y component and an x component, like that. Alright? This angle down here, the tilt of the roadway, will be the same as that angle up there at the top. That angle right there will always be the same as this angle right here. So what that means is this is actually the opposite, and this is the adjacent. And if I want that, I got to use sine. And if I want this one, I got to use cosine. So what we're going to do, this is a two-dimensional problem. You got to do 2 dimensions for it. When I look in the x direction, then I would get, I've got that little component, the x component of the normal force. That's going to be equal to F times the F sub n sine theta. And I want that little push toward the center of the curve to do everything for me. So I need that to be equal to F sub c, which is mv squared over r. Okay? This is that little x component. It's got to get me all the way through the curve without turning my wheel, without friction of the wheels, anything like that. In the y direction, I've got that normal force, right? Right here, the ramp is pushing straight up, and to the left on this, the straight up part would be Fn cosine theta, and that's got to cancel out the mg right there. So I can write both of those things right there, and we're going to pull a little trick here. Since I've got 2 equations with 2 unknowns, one way to do this is to take the first equation, and divide the left-hand side by the left-hand side of this one, by the second one, and the right-hand side by the right-hand side, like that. Okay? We can divide both sides of an equation by the same thing, and since this is equal, then this is the same thing as that, and if I divide both sides, I'm okay. Alright? The normal force cancels. Sine over cosine is tan theta. The mass on top cancels the mass on the bottom, and that g inverts and multiplies to sit with that, and you get this thing right here that's called the bank angle formula. Alright, so if you see the word bank angle in a problem, this is what you want to do. Whip out this equation right here. We're looking for the velocity, so I need to solve this. I'm going to multiply both sides by GR. That's going to be V squared. And I want V, so I would need to take the square root of GR tan theta, like that. All right, and you got all those numbers there, so that should be fine. Okay, car can just make it around a curve with no banking. See how this is just a nice flat curve. 42 meters per second when the road is dry, and mu equals 0.17. What happens when it rains? Well, everything gets a little bit slipperier. There's less friction, so you got to slow down. This guy needs to slow down. Let's find out how much. Here's the car on the curve, and it says that the car is going 42 meters per second when mu equals 1.7. Now, in order to make it through that curve, I've got to have a centripetal force, and I'm getting that from friction. Okay? The friction of the tires on the roadway is what makes me get through that curve. If all of a sudden the friction goes away, the car is going to slide out and end up in the ditch here. That's bad. So if I write F sub C equals F sub F, F sub C, of course, is mv squared over r. The friction on a flat surface is mu mg. And the mass of the car cancels, and I could come through here. I've got V, I've got mu, I've got G. I could solve this for R. So let's move everything around like so. And this will give me the radius of the curve. It's not what I'm looking for, but it's a new piece of information that will help me get what I want here. 1.7 is the coefficient of friction, and G is 9.8 meters per second squared. So that's going to be the first bit of this. I'm going to turn my phone off here because text thing's going crazy. Let's see what that is. Almost done here, by the way. 42 squared divided by 1.7, also divided by 9.8, is 106 meters. Okay? Again, not what we wanted, but it's a useful piece of information. From the center of this curve to the car is 106 meters. All right, that's R. What we need to do now is to let it rain. So here's the roadway on a rainy day in the car. I just learned that this is 106 meters, but my coefficient of friction goes down to 0.9, so I want to find the velocity like that. Well, it turns out I can reuse the same expression right there. Probably better to start here. The physics is the same, the force diagram, everything. So let me just copy that again. And V squared over R equals mu G. This time I'm looking for V, so we'll multiply by R. That would be V squared, so I need to take the square root, and it would look something like that. And the number that I'm going to get here is square root. The coefficient of friction goes down to 0.9. I need to multiply that by 9.8, and the radius, 106, would be 30.6 meters per second. That's slowing down pretty significantly from 42 down to 30.6. If you don't slow down, you're going to slide off the road and get hurt. Okay, so good life lesson there. Lots of people in Columbia could use that. That's actually the last one for today. Let me know if you have any questions. We can Zoom, we can chat, whatever. But that's that. Thank you so much. Have a good day.